Hello, Zoom people. I don't know if it's muted or not.
No, you're good.
I think it's muted.
You're good. We can hear you.
How's your weekend, Professor?
It was good. Yeah, I was just telling Dr. Wang, I saw the Batman movie over the weekend.
Oh, nice. You had 3 hours to spare?
Yeah. Yeah, we saw it with some friends. We've been planning it for a while, so it was nice.
That's cool.
It was good. I was skeptical of Robert Pattinson, but I thought he did a good job.
Yeah, I felt the same.
My favorite Batman? It's so hard to tell because it's like the new one's just so fresh in my mind. Yeah. I think the Dark Knight will always have a special place in my heart, but I think I have to wait a couple months or two to see.
You know what's funny about saying that is that after watching the new Batman movie, I went back and tried watching the old ones. Not the old ones, but like not George Clooney ones, but the ones with Christian Bale.
Yeah.
And it's like, I just think they're just really different films.
They are.
They're
very
really
different.
Like, you can tell like that one's more geared towards, like, I guess like a Marvel type audience.
Yes.
Whereas like the newer one is like much darker and sinister,
Yes.
crime fighting type thing. So
Yes. Yeah.
it's kind of hard to compare the two.
It is. Yeah, but I think I saw the Dark Knight at like at a time in my life when like I was really wowed by those things. I think now that I'm a bit older, like I'm a bit more cynical of those. I'm more critical, I think, and so it's easier for me to pick up on the flaws. Where I think if I rewatched the Christopher Nolan ones, I think I would pick up on a lot of things that I wouldn't nowadays.
Exactly
That's why I'm scared to rewatch them because like it holds such a special place in my heart.
Like, I'd rather keep it in my mind as being like special. As
Exactly.
You know? Yeah.
Exactly. All right, it's 5:30, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing on this very bright 5:30 because of daylight savings? I'm a little bit tired, honestly. Like this time of year, it always takes me a while to adjust, and so I might be a little bit out of it today, but so I apologize. But how's everyone doing besides that? Good, good. Good. So so probably most of you have noticed already, but I've graded your midterm exams, and so I do have them here, and so I can see that a lot of people are virtual, but that's okay. And so if you're here in person, you can pick up your exam after the class. I'm going to bring them back to my office, and so if you want to stop by my office sometime this week to pick it up, then you can do that. Okay. I do want to make sure I get you your exams back because I did try my best to write as many comments and feedback as I could. And so if you're not able to come to campus sometime this week to pick it up, I can scan it for you. But I would prefer not to have to do that for too many people. And so if you can't come to campus sometime this week to pick up your exam, even if it's not office hours, I am in my office for a lot of the day. And so you just knock on the door and I'd be happy to give you your exam. But if you can't make it to campus anytime this week, just let me know and I can scan your exam. So the average you can see on the bottom of the screens, the average was about just about a shade under 41 out of 50. And so you guys did really well. And so that's a fantastic average, for a class like this. So, I was very happy with how you guys did. Okay. And so I think that's all my announcements. Question.
Just out of curiosity, what did people miss the most on the evening?
Oh,
Spread out.
it was a little bit spread. I didn't notice anything particular. Different people kind of miss different things. So, yeah, sometimes there are like certain questions that I notice people messing up on, but I think this one, it was kind of just a little bit everything. So, and that's good. And so I think that's overall, it seemed like people were getting most parts of the exam, which was good. Oh, I will be posting solutions, and so I do have the solutions in my office, and so I will be posting that. Probably not tonight because it'll be a little bit late. But first thing tomorrow, I'll post the solution so you can go over them. Okay. And there are two versions of the exam, and so if you're looking at the solutions and the questions don't match up, it's because you probably have the other version. You just need to scroll down a little bit. Okay. Homework for the next homework is posted, and so I think I'm pretty sure I posted that already. And so that's going to be due next Friday. And so next week is the last week we have before break. And so I wanted to make sure I don't have anything due, immediately after the break. And so I'm having it due, the last day before the break. Okay. It'll give me some grading to do over the spring break. Okay. And so I think that's all my announcements. And so are there any questions I can answer before we get started? Oh, nice. You're going to Hawaii. Yeah, that'll be nice. Okay, all right, so let's go ahead and pick up where we left off. And so we're right in the middle of talking about time marching schemes. Okay. Right, and if you remember, these algorithms were used to solve for unsteady problems. Because up to this point, we've covered convection, we've covered diffusion, but we haven't added the unsteady element to it, right? Or I guess we have for the last couple of lectures, but before the midterm, we haven't done anything unsteady. And so I think right before the midterm, we were talking about 2D problems. And so we had talked about implementing the explicit Euler method in 1D, the implicit Euler in 1D. And so kind of right before we took the midterm, we were talking about how do we extend these methods to 2D problems. Okay. All right, so let me go ahead and write out our full conservation equation in 2D for us. And so first we have our unsteady terms. We have partial phi partial t plus u partial phi partial x plus v partial v partial y is equal to k partial squared phi partial x squared plus partial squared phi partial y squared, okay, plus q of x y. Okay. All right. And so the first thing we were going to do we're going to take this equation, discretize it, and so we're going to apply finite differences to all our derivatives And we're going to do an explicit Euler time marching. And so that means for all the spatial derivatives, we're going to apply a time index of n. Okay, so let me go ahead and write those out. And so I'm gonna basically replace every single derivative here with their appropriate finite difference approximation. Okay, so let's start with the time derivative. And so for the time derivative, we always do the same no matter what. And so we're always going to do basically a forward difference cube for that. Okay. And so since we're in 2D, we have two spatial indices. We have I and j, but our time index is going to be n plus 1. Minus the same phi ij at time index n, and we're going to divide that by delta t. Okay. All right, next we have the convection derivative, and for the convection derivatives, I'm just going to assume that it's that's going to be stable, and so I'm going to use central difference for this. Let's write the derivative again. And so for partial phi partial x, that's phi I plus 1 comma j minus phi I minus 1 comma j, okay, all over 2 delta x. Okay. And since this is explicit Euler, we're going to apply a time index of n on these. Okay. It's going to be n, it's going to be n. Okay. Next, we have the same thing, but for y. And so for our y derivative is going to be v phi I j plus 1 minus phi I j minus 1 all over 2 delta y. Okay. And these are both going to be applied at time index n. Okay. Then we have our diffusion terms. And so first we have the x diffusion term. And so that's going to be phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j all over delta x squared. Okay, that's our diffusion derivative. And just like we have been doing, we're going to apply a time step of n. Okay, and then we have the same thing for y. And so we have phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1, all applied at time step n, divided by delta y squared. Okay. All right, and then to that we have our source term. So it's a lot of terms, and so we have a lot going on here because we have our full unsteady conservation equation with convection, diffusion, source term. Everybody's in. The gang's all here. Okay. All right. And so the next step in this derivation is that we're just going to simplify this. Okay. Or I guess not so much as simplify, but just kind of rearrange the terms in a way that's useful for us implementing code. Okay. And so the way that we simplify this is that we take all the terms with phi n plus 1. Okay. We're going to put those on one side of the equation. And then everything that's at n, we're going to put on the other side of the equation. Okay. Plus any extra stuff, okay? And remember the idea behind doing this is that, remember phi n plus 1, this is the solution at the next time step, right? Where the solution at the next time step is unknown, okay? And so that's what we're solving for. So that's why we put it all on one side of the equation. Whereas the solution at time step n, that's the current time step. And since it's the solution at the current time step, we know this already, okay? And so we want to basically rearrange the equation to put everything that's unknown on one side and everything that's known on the other, okay? And so we make kind of a function of you know, everything that's known, everything that's unknown as a function of what's known, okay? And so I'm going to skip through a lot of the algebra, you know, but you can kind of, you know, rearrange this. But the principal thing that I do here is that in order to kind of isolate this phi n plus 1, since we only have one, is I'm going to multiply both sides of the equation by delta t, okay? And so if you do that, and then you kind of do, you know, all of the algebraic rearranging that I talk about, you end up with this equation here. All right. And so on one side of the equation, we have phi I comma j at n plus 1. And so we just have 1 here because it's explicit. And then we have everything else here on the right. Okay. All right. So we have u delta t divided by 2 delta x plus k delta t divided by delta x squared times phi minus 1 comma j at time step n, okay, plus a minus u delta t divided by 2 delta x plus k delta t divided by delta x squared phi plus 1 comma j at time step n. Okay. Notice how I'm arranging these terms kind of very similarly to how we've arranged terms for other methods, right? And so by that I mean, you know, I'm grouping terms as like coefficients for the certain phi terms, right? So all the phi I minus 1 terms are grouped together, all the phi I plus 1 terms are grouped together, and so that they end up being coefficients in a matrix, right? And so remember, we like to put everything in matrix form here when we can, just because it helps make our, you know, our arithmetic easier. And so putting things in terms of these coefficients makes a lot of sense for that. Okay. All right, so next we have the j minus 1 term. And so this j minus 1 is going to be v delta t divided by 2 delta y plus k delta t divided by delta y squared. This is phi I j minus 1 to the n plus minus v delta t divided by 2 delta y plus k delta t divided by delta y squared phi I j plus 1 at time step n. Then we have the phi I comma j term. And so this is a minus 2k delta t divided by delta x squared minus 2k delta t all over delta y squared plus 1 phi I comma j at time step n plus qi comma j times delta t. Right, so this formula here, you know, and I kind of hesitate calling it a formula, but you can plug into this. This is basically our explicit Euler time marching scheme for 2D problems. In particular, you know, this is our convection diffusion, unsteady convection diffusion. Okay. All right, it's a doozy, and so it's a lot. But you know, what you'll see hopefully is that next we're going to do an example. What you'll see is that you can basically just take each of these equations for the coefficients, because you know we know that these are coefficients in a matrix, and we can just input these equations directly into the code. Okay. And so, you know, I think this is kind of the point in the class where like it kind of starts to click, I think, for a lot of people, you know, why we're doing things in MATLAB and why, you know, why we kind of rely on it so much, because, you know, for this, you know, for something like this, you know, this looks kind of intimidating for, you know, for, you know, just a regular old Joe to, you know, to compute on their own, right? But for MATLAB, complicated equations are, are just kind of another Tuesday for them. And so, as long as you can kind of formulate these equations in MATLAB, then MATLAB can kind of do, basically all the heavy lifting for you and compute this solution much more easily than before. Okay. Any questions on this before we jump into the example? Okay. All right. So let me write out the example, and then we'll jump into the code after that. Okay. And so here we have a 2D problem. And so we have a domain that looks like this. Okay. All right. And so let's say that we have 30 grid points in the X direction and 30 grid points in the Y direction. Okay. And we're going to have Dirichlet boundary conditions all around. So we have phi is equal to 25 on the bottom and the right, or the south and the east side. And then phi is equal to 50 on the west and the north. Okay. And the equation that we want to solve is the following. So we have partial phi partial t is equal or plus 50 partial phi partial x plus partial phi partial y is equal to 3 partial squared phi partial x squared plus partial squared phi partial y squared plus 3xy. Okay. All right. And so starting from a 0 initial condition, okay. And so remember, initial conditions are what the solution looks like at the beginning of our simulation. Okay. And so a 0 initial condition means that we're going to assume that our solution starts at 0 everywhere. Okay. Okay. And then what we're going to do is we're going to compute the time evolution of our solution phi basically as a function of time. So we have phi of x comma y, and since this is unsteady, it's going to be as a function of t as well. Okay, so before we jump into the code, I do want to list out some parameters. Okay, and so some of these parameters are going to be read straight off the equation. Okay. And so let's start with the convection velocities. And so we have a u. So remember, u is the convection velocity in the x direction. And so from this equation, we can see that that value is 50. The convection velocity in the y direction, v, is going to be the coefficient in front of partial phi partial y. And so we can see that's 1. Okay. Our diffusion coefficient is the the number in front of our diffusion terms. And so you can see here that's 3. Okay. And so those are all the terms that we can read straight off the equation. But since this is a time-dependent problem, we also have to define the time step size. Okay. And so that's going to be our delta t in the problem. Okay. And so usually for these kinds of problems, I'm going to give you delta t. There are ways to estimate it, and there are ways to kind of smartly choose it. But we're not going to get too much into that class. And so kind of the approach that I'm going to take for this class is to assign a delta t that's small enough, to give you a good solution. Okay. And so the delta t that I'm going to pick is 0.0001 seconds. Okay, so 0.1 milliseconds. Okay. The zoom's kind of lagging a little bit. And the number of time steps is going to be 250. All right. Okay. So any questions on the problem setup? Okay. All right. And so since, well, I mean, I guess I didn't mention it yet, but we're going to be using explicit Euler because we haven't learned implicit yet. Okay. Yes, yeah. So delta t is going to be given to you most of the time. Yeah. There are ways that you can compute it, or there are ways that you can estimate it, but that goes a little bit beyond the scope of this class. And so for everything that I'm going to have you guys do, I'm going to give you delta t. Yeah. Okay. And so since we're using an explicit Euler method, we're going to get a system that looks like the following. And so we have phi comma j at n+1, right? And so that's essentially what we have up here, right? So phi comma j at n+1. This is going to be equal to a coefficient matrix A multiplied by phi comma j at n, okay? Where the coefficients in this matrix are going to come from our time marching equation. Okay. And then to this, we're going to add an additional function right here, where this additional function is going to take into account, in this case, we do have a source function. And so the source function is going to be part of B, and also our boundary conditions are going to be part of B as well. Okay. But remember, the hallmark or the distinguishing feature for explicit time integration is that we don't have to do any kind of inversion or any kind of linear solve. And so all we have to do here is that once we've determined the coefficients of A, we just multiply it by the known solution, and then we add to it. Okay. And so there's no backslashes, there's no linear solves involved at all. We just have matrix vector multiplication and matrix vector and vector addition. Okay. And so that is really, really cheap. Okay. And so next I'm gonna download the code. And so the code's gonna be available to you online. So I'm going to download that code and kind of show you the different features of the code and run it so you can kind of see what's going on. But before I do that, are there any other questions on this? Everyone have everything written down, because I'm going to switch to the MATLAB here. Okay. All right. So let's go ahead and switch. Okay. And so go to I apologize. I should have been prepared for this. Okay, yes, continue. I've already uploaded my booster. Why does it keep asking me? 417. Okay. Let's go to this week. Okay. And so I have 3 scripts that I want to share with you this week. Okay. And so let's start with this first one. And so this is going to be the one that we're going to work with first. Okay. And so while that's loading, and so it's going to take a little bit of time for MATLAB to start up, let's go over the different features of this code. If the MATLAB splash could go away. Okay. So let's look at section 1 first, because we can see kind of section 1 peeking out from behind the MATLAB splash screen. Okay. And so the first section, just like all the codes that I've given you, the first section of the code is just we're going to define our variables. Okay. And so all the parameters of the problem we're going to define up here. Okay. And so first you see that we have Lx. Lx is the length of the domain in the x direction. And so you can see that's 1. Then we have Ly, which is the length of the domain in the y direction. And so that's 1 as well. Then we have the number of grid points in the x and y direction. So that's 30. Okay. We have the total number of nodes. We have the grid spacings. And so all of that is pretty standard. Okay. Next, you can see here, we're defining the different parameters for this problem. And so first we have VISC, which is our diffusion coefficient K. Okay, so we can see that's equal to 3. Next, we have the x velocity, which is 50, the y velocity, which is 1, and then we have the time step size as well as the number of time steps. Okay. Okay, and so this is kind of in what I think is kind of good style for these kinds of codes. Okay, because we have a lot of parameters here, and so we have a lot of things that we need to keep track of. And so, for me, it's always good to kind of define these at the beginning of the code, just so that you're aware of what all the parameters are. and label them, and so that you know exactly what they're what they're meant to do. Okay. And so that's why later on in the code we should change very little. Okay. And so if you wanted to make changes to this code, and so let's say that you want to change the number of the number of grid points, or you wanted to change the convection velocities, you can do so very easily at the top of this code here, without having to change any of the algorithms down here. Okay, and so MATLAB is loaded, and that is obnoxiously big. Okay, and so let me go ahead and pull it out. Okay, so that's very big. So let me go ahead and change that. Wow, 36. Okay, so can everyone still read the code okay when I pick a size 14? Is this size is okay? Okay. Okay, so let's jump into section 2. Okay, and so section 2 here is we're going to fill out the coefficients in matrix A and B and the vector B with the proper coefficients. Okay, and so for this we're going to use our time marching equation. Right? Okay, and so first thing you see here is that we have a nested for looping. We see we have a loop on I and a loop on J. Right? And so this is true to form for all of the 2D problems that we had. Because for all the 2D problems, we need to visit every single node in our grid. Okay. And also very similar to our 2D codes, we have to compute the proper IDs. And so we have the ID numbers for my ID, the left ID, the right ID, up and down. Okay, so all that is the same as before. Okay. And so next thing we're going to do is we're going to set the coefficients in the matrix. Okay, and so again, this is similar to most of the 2D problems that we've done, except now the formulas for the coefficients are going to be different. Okay. And so let's go over the equation for the left ID. Right, so we have A at my ID comma left ID, and so we know that this is for the phi at I minus 1 comma J, right? Because it's the left neighbor, and so the I is minus 1. And if you go back into your notes, if you look at our formula for it, you can see that the coefficient for this is u delta t divided by 2 delta x, right? And so we have that part of the equation right here. So we have the x velocity times dt divided by 2 times dx, right? And then to that, we're going to multiply by k delta t divided by delta x squared. Okay. And so you can see here, I have that formula coded up as well. Okay, so we have this times dt divided by dx squared. And so if you go along the line of each of these, you can see that each are very similarly defined according to what their equation is for the time marching scheme. Okay. All right, so this part's really important here. So this is kind of a key part of this algorithm to make sure the coefficients match up. And so are there any questions about how I define this? Okay. All right, and so now that each of those are defined, we have to define the the source function as well. Okay, and so for our source function, and I don't know why this is here. Okay. And so our source function is going to be 3 times x times y. Okay, and so you can see here I'm using the code to compute what the x position is, and so that's going to be x sub I, and y position here is going to be y sub j. Okay. And so you can see I'm computing those in the same way that we've done before, where we take the I index and the j index, so we multiply them by the appropriate grid spacings. Okay. And then our formula is 3 times x times y, and then we have a dt that comes out as well. Right? And so I think in the ones that I posted online, I have a 0 here. And so if you want to take out the source function, you can multiply that by 0. But for now, I'm just going to leave it in. Okay. Okay. All right, and so that takes care of all the interior nodes. And so next we have our boundary conditions. Okay, so our boundary conditions are all very easy at this time because they're just Dirichlet boundary conditions. Right? And because we're doing explicit Euler, the way that we apply the Dirichlet boundary conditions is that we just implement its value in the right hand side vector. Okay, in B. And so you can see here for the left boundary, we apply our boundary condition of 50 in the and we're also initializing our solution to be that value. Okay. And so remember, sol cur here, that's our phi at n, right? So this is phi at n. Okay. And so the reason I'm doing this at first is to basically just to ensure that our initial condition satisfies our boundary condition. Okay? So you don't have to do this. And so if you don't do this, then the boundaries are just going to start out at 0. And that's fine because it's going to evolve anyway. But this just makes the initial plot look a little bit nicer. Okay. Just to make sure that all your boundary conditions are being satisfied. And so we do the same thing for for the top and the right and the bottom. If you notice here for these boundary condition loops, I don't make any modifications to the A matrix, right? And so why is that? And so normally when we compute the boundary conditions, and for a Dirichlet one, we also have something like this, right? Right. And so all up to this point, we've always basically made a modification to the A matrix as well as the forcing vector. Okay? But for explicit Euler, we don't have to do that because remember, for explicit Euler, we're not solving a linear system of equations. All we're doing is just a matrix vector multiplication, and so we don't need to do this. And so the only thing that we need is just to make sure that the phi value is going to satisfy the conditions. And so that's the reason why we don't have anything for the A matrix here, because it's explicit Euler. But for implicit Euler, you do need to modify the left-hand side matrix. Okay. All right. Any questions on this? Okay. All right. And from there, so after we apply the boundary conditions, now we move forward into time stepping. Okay. And so for time stepping, what we have here is a loop, okay? And so we're going to loop over all the time step values. And so we're going to loop from 1 to nt. And the way that we're going to compute Sol next is we're going to take our coefficient matrix A, we're going to multiply it by a current solution, and then to that we're going to add B, okay? So basically the same as what I have in the notes, right? And so we have our coefficient matrix, we multiply by the known current solution, and we add B, okay? And then after we compute that, then we update the current solution to be what we just computed. And then we go back to the loop. Okay. And so for this particular problem here, just to kind of illustrate what's going on, I have this additional code here for plotting. And so, you don't need to know too much about how this code works here. But I basically set it up so that I only plot every 10 time steps. Okay. Because we're solving this equation for 20 or 250 time steps, and so if we produced 250 plots, that actually might crash this computer, and so I don't want to crash this computer, and so I only plotted every 10. Okay, and so when I run this code, 25 plots should show up, and then from those 25 plots, you should be able to see the time evolution of the solution in this domain. It'll make a lot more sense once I run it. But before I run it, are there any questions before we hit go here? All right, so get ready for pop-ups. And so this is like your computer back in the 90s when you're searching for unsavory things on the internet, and you go to a website and a bunch of these pop up. Our question: so wouldn't it be easier to set as an animation? It is, but for this one, I chose to actually plot all 25. And so you can see frame by frame what's going on. Okay. And so here is the solution. Let me go ahead and move this down here. Okay. And so you can see this is frame 25, and so this is what it looks like at the end. Okay. And just the way that these are stacked on top of each other, I'm just going to close this, and so you can kind of see the animation playing in reverse. Okay. And so think of this solution here as kind of the steady state, and so this is what the solution looks like at the very end. Right. And so you can see here we have our boundary condition of 50 on the left and the top, and our boundary condition of 25 on the bottom and the right. Okay. And then as I start to close these, you'll start to see it change over time. Okay. But remember, we're going backwards. And so this is the end solution. And so I'm gonna show you, what it looked like at the beginning, but kind of going backwards in time. Okay. So let me close this. Okay. And so at first you're not going to see that much change because this solution reaches steady state pretty quickly. But you can start to see that it's starting to change a little bit. Okay, so you can see that this part here is kind of pushing in. Okay. Okay. Right. So now we're getting about about a tenth of the way through the simulation. And so you can see here that a bunch of the results here are at 0, right? Because remember, we started everything at 0. But as time went on, then then the solution kind of propagated to that 0 part. Okay. Okay, and so this is what the solution looked like at the very beginning. Okay, so at the very beginning, you can see here that we have just satisfied our boundary conditions here. Okay. But most of our solution here is just blue. It's just 0. But over time, due to the convection and due to the diffusion, then our solution at the boundary is kind of penetrated into the middle. Okay. And so if you kind of think of the figures that we just did, but kind of view them in reverse, that's what it would look like. Okay. All right, and so I do have some MATLAB scripts that actually produce movies, so that's actually easy to see. But I'm saving those for later because this is actually it's actually a pseudo steady problem because even though we're solving it as an unsteady problem, none of the parameters actually change with time. So none of the boundary conditions, none of the velocities, or none of the diffusion coefficients actually change. And so it doesn't make for the most exciting animation. So I save the animations for kind of the next set of lecture notes, which we're going to go over, which we're going to go for next. But that's the essential details for this implementation. Okay. And so to implement, so to kind of recap, so to implement an explicit Euler solution, what you need to do is you need to basically define all the coefficients in your matrix A. Okay. You need to implement your boundary conditions inside the vector B. Okay. And then you need to march it forward in time. And so the marching forward in time involves just a direct matrix vector multiplication and then a vector addition. Okay. And then you just kind of update your solution based on that equation. And so it's basically the exact same process that we followed for the 1D problems, before we took the midterm. It's just that now it's extended to 2D because it's it's a 2D problem. Okay, but all the principles are still the same. It's just their matrices are just a lot bigger. Okay, any questions on this?
Yeah, quick question.
Yep.
So instead of doing that update notation for the A matrix,
Yep.
We're basically doing a different type of update notation towards the end of it.
Yes. Yeah. So in this case, the A matrix doesn't change its value, and so the coefficients in the A matrix are kind of staying fixed with time, and so we don't need to update its values, and we only set their values once. And so this update here, this is a little bit different from the update notation that we've used before, because we're actually updating what the solution actually looks like. And so we're not, and so we're actually using 2 different variables to store the 2 solutions. Yeah.
Okay, thank you.
Mm-hmm. Any other questions on this? Okay. All right. So I'm going to bring back the iPad. And if you read the lecture notes, I basically inputted the pseudocode into the lecture notes. And so you can kind of read some of the logic that we just went over as well. Okay. Okay. And so that's explicit Euler. And so I do want to go over very quickly implicit Euler. Okay. So I'm not going to go through the whole derivation, but I'll show you kind of how I got it. Okay, and so let me scroll up a little bit here. Okay, and so here is our equation. Oh, not this one. This one. So here is our our discretization of our conservation equation. After this is just directly after we plugged in the finite difference. Okay, and so remember the big difference between explicit Euler and implicit is how we treat the spatial derivative terms. Okay. And so for all the spatial derivatives, so like partial phi partial x, partial phi partial y, this one and this one, right? You can see here from our discretization when we plugged in their finite difference approximation, we evaluated each one at time step n. Okay, because that's what you do for explicit. Okay? But for implicit, what we do is that instead of evaluating these at n, we evaluate everything at n plus 1. Okay? So I'm not going to write down kind of this whole thing again because it would be kind of a repeat, but it does change what we do on this next step, right? And so because we're evaluating everything at n plus 1, all the spatial terms, it changes how we're going to do this rearranging, because we still want to aim for something like this, where we have all the n plus 1s on one side and all the n's on the other, right? And so that goal is still the same. The difference here is that we have a lot more n plus 1s than we do n's, okay? And so our implicit Euler equation actually looks kind of the opposite of this, where all of these terms here are actually going to be on the other side of the equation. Okay, so I'm not going to go through the whole derivation, but I do want to give you the final result because we are going to use it in the next set of lecture notes on time marching schemes part 2. Okay. And so by assigning spatial derivative terms to n plus 1, okay, and if we rearrange the terms like we usually do, we end up with the following time marching scheme. Okay? So we have a minus u delta t divided by 2 delta x minus k delta t divided by delta x squared. This is phi I minus 1, comma j, n plus 1. Okay. Then we have a u delta t divided by 2 delta x minus k delta t divided by delta x squared. Okay, and that's phi I plus 1 comma j at n plus 1. Okay, plus the minus v delta t divided by 2 delta y minus k delta t divided by delta y square phi I j minus 1 n plus 1 plus v delta t divided by 2 delta y minus k delta t over delta y squared. Okay, phi I j plus 1 n plus 1. Okay, plus 1 plus 2k delta t divided by delta x squared plus 2k delta t over delta y squared phi I comma j n plus 1. Okay, so that's everything on the left hand side. And on the right hand side we have just this. Okay. So the right hand side we just have a singular phi I comma j at n and then a qij source multiplied by delta t. Okay. And that is our implicit Euler time marching scheme for 2D problems. All right. And so, it's a lot of terms again, but again, if you kind of follow the format of, of the terms that we've, of the code that I just provided you, then, you can see that a lot of these terms, even though they look really intimidating here, once you kind of input them in MATLAB, they become very simple to do. Okay. All right. But of course, the big difference here for implicit problems that, we don't have a very simple matrix vector multiplication anymore. Okay? Because now, we don't have a straight up equation for phi I comma j n plus 1. Okay? Because we have everything, we have too much stuff on the left now. Okay? And so the format, after you kind of input everything into coefficients and everything, the format for the implicit Euler looks like the following. And so we have our matrix A is now going to be on the left-hand side. Okay, so we have phi I comma j n plus 1 multiplied by A on the left. This can be equal to phi I comma j at n. Okay. And this is going to be plus B, okay, where the B is going to account for the boundary conditions and the source term. Okay. Okay. Where that A is still our coefficients matrix. And then to solve the system for phi I comma j at n plus 1, what we have to do is actually invert the system. Or in other words, one way that we can say this is that we're solving a linear system of equation. And so that's basically the same as what we have been doing. Okay. Right. And so basically what we have is we have phi I comma j at n plus 1 is equal to a backslash. Okay. And so I'm going to use kind of pseudo MATLAB notation here. Okay. So it's going to be a backslash phi I comma j at n plus b. Okay. And so in terms of actual typing, in terms of what you develop, right? Of course, your code is going to look different for implicit versus explicit, but the difference is actually not going to be that big, okay? Because for explicit, remember the key point for explicit was the following. Okay, and so for explicit, we had phi I comma j n plus 1 is equal to a multiplied by phi I comma j at n plus b. Okay. And so that was our explicit Euler time advancement. Okay. And so instead of a star, what we have instead is a backslash. Okay. And so, in terms of what you implement, it's not going to be that different, but you will notice it in terms of time. And so the backslash here is a lot more expensive than the multiply. And so what you'll see is that your implicit codes will run a lot slower than your explicit ones. Okay. All right, question in the chat. So why would we use explicit or use implicit? Explicit looks easier to use. It is easier to use. And so, generally speaking, actually explicit is actually used for a lot of big codes out there as well. So I know ANSYS has an explicit solver. A lot of the codes I've worked on have explicit solvers as well. They don't use explicit Euler, but they use kind of a spin-off that has better properties. And so explicit is easier. But the downside of an explicit solver is that you might run into unstable solutions. Okay? Right, so you kind of run into the same issues as what you ran into with central difference for convection. And so if you use explicit, that's totally fine. And so you can solve a lot of great problems with explicit. You just have to make sure that your delta t or your time step size is small enough. Yeah. usually, for most physical processes, bless you, for most physical processes that we work with in mechanical engineering, like heat transfer situations, this is used for a lot, mass transfer situations. If you use a time step size of about a millisecond around that area, then I'd say most cases are going to be really good. But there are some situations like if you're going to run a simulation on a combustion engine, a combustion reaction happens really, really quickly. And so if you want to use an explicit scheme for something like that, you have to be really careful with the time step size. Otherwise, your simulation is going to blow up, literally. And so if you don't want to worry about unstable solutions, then implicit is the way to go. But implicit is actually quite rare in practice because it is very time consuming. And so that's kind of a long-winded answer to your question. Yeah. Okay, any questions on this before we move on to time marching part 2? Okay. All right, so let's go ahead and move on. And so this is literally the lecture notes is time marching part 2. And originally when I had developed this class, I didn't plan for this to be another set of lecture notes, but it does cover a neat subset of problems that I think is worth covering in its own set of lecture notes. And so this is kind of an extension of our time marching schemes, but it's going to be for situations where the parameters or the boundary conditions actually change with time. Okay. And so far, we've covered the two main time marching schemes. We have explicit Euler, implicit Euler. Okay, so those are great, but we haven't really used it for anything cool yet. Right? And what I mean by that is that we've basically been solving steady problems with time marching schemes. Okay. But that seems like such a waste because if we are going through all this trouble to develop these time marching schemes, we should use it for things that actually change with time. Okay. And so that's what we're going to cover here. And so we're going to cover, situations that actually change with time. And I think more importantly, how do you incorporate that into MATLAB? Okay. Okay. And so for this set of lecture notes, just because I think they produce nice animations, I'm going to focus mostly on sinusoidal time variance. Okay. And so I think in the first example that I'm going to do, I'm going to have a boundary condition that oscillates with time. But you can also have things like convection velocities or diffusion coefficients that change with time as well. And they produce, some really cool looking simulations. Okay, so let's go over some examples of this. And so what are some examples of physical processes where the features of the process actually change with time? Okay. I think this is always important to do because even though we're diving deep into the mathematics and we're diving deep into numerics, it's always good to remember that we're using this for physical problems. And so it's always nice, at least to me, to think of what are some physical problems that kind of fit into these categories. Okay. All right, so one example that works really well is the process of annealing. Okay. And if you're not familiar with the process of annealing, the way it works is that it's basically a repeated cycle of heating up a material and cooling it down. Okay. And this repeated cycle of heating up and cooling down will ultimately strengthen the material. Okay. And so that process of, heating it up and then cooling it down, the temperature of the material is going to fluctuate up and down. Okay. And so that's an example where, we can modify that, or we can simulate that with a boundary condition that changes with time. Okay. Number two. And so number two is a situation where you have pollution transport in the atmosphere. Okay. Pollutant transport in the atmosphere where the wind patterns change with time. Oh, zoom. Okay, there we go. Something wrong with the Wi-Fi in this. Okay. And so, if you walk out on any windy day, you know that the wind patterns will change with time, right? And so we can model that fact by, using a time-varying convection velocity. And number three, one more situation is one where we have, maybe a piece of metal that's suddenly cooled by dunking it in a tub of water. Okay. All right. And so that's a situation where, the boundary conditions will change, very, very suddenly. Okay. And so what you'll see is that the consistent factor, or the connecting thread behind all of these situations, is that now we're going to have time actually show up in our equations. And so T will actually make an appearance. Okay. All right. And so conceptually, it's not that hard to imagine it. Yeah, things are going to change with time, and so we should have T as part of our equations. Okay? I think the difficulty with this section is how do we actually incorporate this in the code? Because it's going to change how we incorporate things. And so the big difference is that since T is going to show up now, we actually have to keep track of a new time variable in our code. Okay. Right. So defining a parameter T is not that difficult, right? I think the part that's going to be challenging, or not challenging, but the part that's going to be new is the updating part. Okay. And so the updating is going to be, what's going to be, I think what's going to be different about this this part. Okay. And so we kind of have to update. You'll see once we do an example, you'll see that this time is going to be updated kind of right alongside our solution. Okay. Okay. And so the define part goes something like this. Okay. And so at the very beginning, we're going to define T, and we're going to set it equal to 0. Okay. Because we'll say time starts at 0. Okay. Then the update part. So inside our time loop. Remember, for every unsteady problem, there's a loop that loops forward in time. Okay, we're going to have an update equation. Okay? And so what we're going to say is that T at n plus 1, or the next value of time, is going to be equal to Tn plus delta t. Right, and so we have to update this time variable so it kind of moves forward in time along with our solution. Okay, but besides that, all of the methods and equations that we've gone over for implicit, explicit Euler, all of them are still going to apply. All right, any questions on this before we jump into an example? Okay, all right, so let's do an example. So let's start with 1D because it's a little bit simpler to do. Okay, and so in this situation, we're going to simulate basically a vibrating string. Okay. All right, so the vibrating string, the equation for that's going to look like this. We have partial phi partial t is equal to 3 partial squared phi partial x squared. Okay. And then to model the vibration, I'm going to have one of the boundary conditions here change with time. Okay. So what I'm going to say is that phi at x is equal to 0, and so this is going to be the boundary condition on the left. Oh, I'm really sorry, Zoom people. The Zoom is being really slow in updating. There it goes. Wow. Okay. It's yeah, it's been really laggy today for some reason. Okay. And so the boundary condition at x equal to 0, comma t, okay, is going to be equal to cosine of pi t, okay. And then the other boundary condition is going to be a constant. So we're going to say is d phi dx at x is equal to 1, comma t. Okay, we'll say it's equal to 2, and so the slope of the solution at the other end of the domain is going to be just 2. Okay. Okay. And our initial condition here is going to be 0. Okay, so we have phi at x and t is equal to 0. Okay, and so we're going to start out with the solution equaling to 0 at the at the outset. Okay. Okay, and so we want to take the system and we want to march it forward with implicit Euler. Okay. Come on, Zoom, update. Come on. Come on. There we go. Okay. All right. And so we're going to use an implicit Euler for this one, and we're going to use a time step size of 0.1. Okay. And so this is going to be our delta t. Okay. Oh, also, so that's the temporal discretization. So that's the time discretization. We have to talk about the spatial one. And so we're going to use a spatial discretization of 5 points. Okay. And our grid spacing is going to be 0.25. Okay. And so our domain, come on, Zoom, come on. Zoom is also tired from daylight savings, I guess. Okay, and so our spatial domain looks like this. Okay. Looks like this. Come on. I think I need to reconnect the Wi-Fi. It's ridiculous. Okay. Oh, come on. I apologize for this. Technical issues. I think there's an issue for the Wi-Fi or something. Wait a second.
It's like the other room.
Uh-huh.
Probably needs to slap.
Maybe. But I can't slap my iPad. I actually own this. But the projector I can slap because I don't own it. Yeah, the other day I was lecturing in the other room, and the projector was having a lot of difficulties, and I wanted to slap the shit out of the projector because it was being really annoying. But I'm really short, and so I can't reach up there without a chair. And so I told the projector, "You're lucky I'm a short man. Otherwise, I'd slap you." What Wi-Fi am I connected to? Let's see. Yeah, it's edit room. Okay. Okay. Let's see. Okay, let me just show you the code then, because that was going to be the next part. Because I think it's working okay here. I hope it works for my next class. That'd be really annoying if it doesn't. Okay. All right, so let me go ahead and share my screen here. Because I do want to play the code for you. Because it is a cooler code. Okay, so here is our code, and so what I was going to show you is that if you actually applied the implicit Euler to our equation, you're going to get a coefficient matrix that looks like this. Okay, and so first of all, you're going to have the coefficients here. Okay, so everything here in lines 2 through 5, or 2 through 4, excuse me. So this is going to be due to the to the diffusion equation, and also due to the time step size. Okay, and in the first row, you can see here that we have a coefficient of 1, and so that reflects the fact that we have a Dirichlet boundary condition on the left. Okay, and on the last row, you can see here that we have 2 entries, right? So we have a 1 and a -1, and that reflects the fact that we have a Neumann boundary condition on that side. Okay. Okay. And so if we advance this forward in time, okay, you can see here that I'm actually producing a video. And so if you run this code on your computer, it'll actually produce an MP4 video. So that's cool. Okay. Right. And so here's the time stepping. Okay? And I've actually implemented it in 2 ways. And so I've implemented it first as a while loop, and I've implemented it again as a for loop. Okay. And so both of them will work, but I wanted to give you an example of both, just so that you can see. Okay. And so the key part to this this whole operation is this right here. Okay. And so if you remember, for implicit Euler, we have a situation that looks like this. So we have phi, or a times phi at n+1. Okay. And this is just going to be I, okay, is equal to phi n, or excuse me, phi I at n, okay, plus b, okay, or this b right here, this b incorporates the boundary conditions, okay, and so you can see here that for the first line of b, I have a cosine of pi t, okay, and that reflects the sinusoidal boundary condition that I've applied on that n, okay. All right, but for all the other parts, you can see here that I have set the b value to be the current solution. Okay, so the current solution. So my current solution is phi at n. Okay, so I'll do this for node 2, 3, and 4. And then for the last boundary condition, we actually don't need to set anything because we set its value up here, and it doesn't actually change with time, and so we don't have to worry about that. Okay. And so you can see here in the code we have our linear solve here. So we say our next time step is equal to a \b. Okay, and the reason we have backslash here is because we have a linear system, right? And so we invert the a, we multiply by that side, and then we update the current solution. Okay. The other thing I want to highlight in this code is this right here. Okay. And so because our cosine term here depends on t, we have to make sure that t is being updated, because if we don't update t, right? So t here starts at 0. Okay. And so before we enter the loop, our time is 0. Okay. But we want to make sure that each time the loop repeats, the t value here actually updates. Okay. Let me clear the drawings a little bit. Because we don't want it to be 0 all the time. Because if this is 0 all the time, then this boundary condition is not going to change. And so what I have here at this part of the code is that each time we reach the end of the loop, we actually have to update the value of the time variable. Okay, so this is why we have t is equal to t plus delta t. Okay, and so here you can see that we use the update notation, that we know from before, right? And so we have the new value of the variable is equal to the old value plus dt plus the increment here, which is dt. Okay, and I have I have this here, although I don't think I actually use it for anything. I think I had this here just for plotting purposes, but it's okay. Okay, so let's go ahead and run it, and you'll be able to see the animation. Okay, so there's our string. MATLAB is struggling. Okay. And so you can see here that the string is vibrating, right? Okay. So I think the animation is done. And if you go to the folder where you ran the code, it might be easier to see in the video, because the video is not going to sputter like this. Okay. And so if you run the video, okay, you can see the vibrating string in action. Okay. Let me play it one more time. And so what I want you guys to pay attention to is actually here on the left, right? So remember the thing that we're defining is we're saying that the boundary condition on the left-hand side is actually going up and down like a cosine, right? And so it's going to start a cosine of pi t, and then it's going to go down to -1 because it's a cosine function, and then it's going to come back up. Okay. And what the rest of the function is doing, or what the rest of the solution, it's basically reacting to this boundary condition here. Okay. So let's go ahead and repeat it one more time. Right, and so it kind of looks like a vibrating string, okay, or a wiggling string. Right? Okay. Any questions on this? Okay. All right. So I apologize again for the technical difficulties. I do want to go over kind of the theory behind this. So I'll do that first thing next time. Hopefully the Wi-Fi is going to Wi-Fi is going to behave a little better. But I'm going to end class a little bit early today so that people here can come grab their exams. So remember, if you want your exam back, I'll be in my office most this week, and so if you want to come by during office hours or any other time really, so I'm in my office most of the day. I get here I try to get here around 8:30, 8:40. So if you want to come into my office and grab your exam, that's fine. If you can't make it to campus this week, I do want to make sure that you have your exam, and so if you can't make it to campus this week, send me an email and I can scan your exam. But I don't want to do that with too many people, because that's going to take me forever to scan a bunch of exams. So and so I would prefer that you guys come pick it up. But but if in the case where you can't come to campus, then just let me know, and I'll scan it for you. Okay. All right. So thank you guys for coming today. I apologize again for the technical issues, and I will see you guys on Wednesday. If you're here, you can come up and get your exams.
Thanks again, Dr. Tran.
Thanks, Chris.
Thanks, Dr. Tran.
Thanks, Eddie. See you later. Damien, DJ, any questions before I wrap up the Zoom session?
Thank you, President.
Oh, no problem. See you guys. Okay, all right. So I'm gonna go ahead and log off. All right.